Hello, everyone. I hope you are all doing great. Today, inshallah, we will start this lecture. I've thought to record this lecture in order to overcome the lectures of next week. As I told you previously, we already started spans and vector spaces. This is really a very important topic and it needs your attention. You will have to focus in this particular chapter. It's not hard, but it has another, I usually like to say, another flavor of questions. It's really very nice, and I will do a recap for the previous lecture. First of all, what's a vector space? We mean by a vector space a collection. It's a collection of vectors or objects under two main operations, the addition and the multiplication by scalar. This definition is already written in this slide. Give me just seconds, I will get my laser pointer. So it's exactly as written. Real vector space is non-empty set, which means it's a set containing some of the vectors or objects. It may be points, it may be vectors, it may be matrices, it can be some operations, whatever. The most important thing that this set is huge enough that it is closed under the addition and multiplication by scalar. What we mean about multiplication and the addition by scalar, the addition closure, it means if you have two vectors or two objects belongs to this vector space, if you add them together, the result also will be in this set. خليني اقولها لك بالعربي. لو انا عندي اتنين فيكتور وجمعتهم على بعض، الريزلت بتاعت الفيكتورز دي برضو موجودة في الست اللي أنا بسميها فيكتور سبيس. فحاجة ضخمة جدا، مجموعة كبيرة جدا من الفيكتورز. Also, the scalar multiplication, it means if you have a vector and you multiply it by a number, the result also will exist in this vector space. So, if you have any vector، لو كان عندك أي vector وضربت الكوردينتس بتاعته في number whatever هو شكله عامل ازاي، النمبرز دي او الفيكتور ده هي belong to the vector space. Of course, these are in details the additive closure or the addition closure and the multiplication by scalar closure. The addition closure, it means the commutativity, it means the distributivity and the associativity of the vectors, as you can see. Also, it has to have, or it must have a zero vector, which is we call it the null vector, or the vector once you have the vector with all components is equal to zero, which represent if you add a vector to its negative value, the result will be the origin. The negative value, it's called the symmetric vector of any vector. So if I have, for example, a vector in R3, which is 2, 3, and 4, the negative vector will be -3, -2, -3, -4. Once you add them together, the result will be 0. So this is really very important. The multiplication by scalar, and all of this we already did go through it previously in the previous lecture, but I wanted to do a recap. Multiplication by scalar, it means if you have a vector and you multiply it by a, where a belongs to the set of real numbers, the outcome also will belong to this vector space. So it's really a very important property. And those are the details, the existence of the identity. So if you have a vector multiplied by 1, the result will be also the same vector, and that's a must. And we already saw in the previous lectures, some of the vectors fail this property. The distributivity of two scalars on vector, the distributivity of a scalar on two vectors, all of this must be satisfied. A failure of any of these conditions will prevent this set to be called a vector space. This is major and this is really very important. Okay, now we will go to another part that was covered previously in the previous session, which is the about the proposition of vector space. So each vector space, it's symmetric. Each vector, it's symmetric, is unique, which means for any vector space, any vector belongs to this vector space. Any vector, it's symmetric, which means the negative values or the opposite values of those numbers already exist in this vector space. يبقى for each vector, it's symmetric, already exists, and unique. So you don't find more than one, and it makes sense. Number two, A times the null vector of V will equal to the null of V. That's for every A belongs to R. The condition after that, if you multiply by a negative value, any vector, it's symmetric, will exist in this set, as we told you. And for AV, it's equal to 0. It means either A is equal to 0 or V equal to 0. For every A belongs to R, and for every vector belongs to the vector space. Those are the propositions related to vector space. Okay, another topic was also done in the previous lecture, which is what's a vector subspace? What's a subset from the main set? A vector subspace, it's apart from a vector space. It's apart from a vector space under these conditions. The conditions are, number one, any subvector space from a vector space should share the origin of the original vector space. يبقى لو عندي فراغ، الفيكتور سبيس بسميه فراغ، سب فيكتور سبيس فراغ جزئي. يبقى عشان يبقى عندي سب فيكتور سبيس فروم فيكتور سبيس لازم يبقى لهم نفس الزيرو، نفس الاوريجين. وللسب فيكتور سبيس لازم الاوريجين بتاعته تبقى هيها نفس الاوريجين بتاعت الفيكتور سبيس. مفيش difference between them. اوكي، برضه closure under addition و closure under multiplication by scalar. خلي بالك ان each vector space of a vector space is a vector space. يعني كل vector space هو نفسه يعتبر sub vector space من نفسه. وخلي بالك ان الفيكتور سبيس is a vector subspace of V as I told you. وان نفس الكومنت a vector subspace of vector space is a vector space. الفيرست statement it means كل set جزء من vector space هي نفسها تعتبر vector space by itself. لانك لو لاحظت هتلاقي ان موجود فيها الاوريجن وموجود فيها التو كونديشنز، بس هي جزء من الفراغ الاكبر. طيب جميل جدا. اللينير كومباينيشن، وده موضوع برضو مهم جدا واتكلمنا فيه المره اللي فاتت. يعني ايه linear combination؟ For any vector space there is a combination between vectors. يعني لأي vector space في مجموعة من الفيكتورز أقدر أجنريت from them other vectors. يعني مثلا على سبيل المثال، وده مثال أنا ضربته برضو المرة اللي فاتت، لو أنا عندي in 2 dimension الفيكتور 2 و 4، الفيكتور 2 و 4 ده I can generate it from 2 times the vector 1 and 0 plus 4 times the vector 0 and 1. So there is generators for vectors, and if I have a linear combination adding these vectors together and multiply each one of them in a number and adding them together, it will develop another vector. And this definition is written in here. Okay. Remember this problem, we already did go through it in the previous lecture, but I wanted to refresh your memory again. Here is asking you, is vector 7, 8, and 9 the linear combination from the vectors u and v؟ يعني بمعنى هل الفيكتور 7 و8 و9 ده اقدر اجيبه او اخلقه من التو فيكتورز u and v؟ طبعا. طيب اتشيك ده ازاي؟ كل اللي عليا اني اتشيك الريليشن دي، انه there is exist K1 and K2 alpha وبيتا x و y لو انت ضربتهم في 1 2 3 الفيكتور الاول وضربت other variable في الفاريبل في الفيكتور الثاني، الريزلت هتبقى 7 8 9. لذلك لاحظ انا عملت ايه؟ خدت الفيكتور اللي انا عايز استدي الكيس بتاعته حطيته in one side، بعدين خدت التو جنريتورز دول كل واحد فيهم ضربته في constant. So it's simply k1 times u plus k2 times v and the result equals 7 8 9. In such a case, I will have a system of equations searching for the values of k1 and k2. And this is exactly what we are going to do. We are going to solve a system of equations, which is a function in k1 and k2, as you can see. So it's a k1 times 1 plus k2 times 4 equals 7. The second equation, 2x1 plus 5x2 equal 8. The third equation is going to be 3x1 plus 6x k2, which equal to 9. Those are three equations in how many variables? In just only two variables. Of course, we already had the solution of a system of equations, so this should be just a walk through a park. Already done. That's the augmented matrix. And I will try to get the reduced echelon form. Those are the values of coefficients of K1 and K2, and that's the results, 7, 8, and 9. Once you try to work out those numbers, reach a reduced echelon form, you will have your solution. So K1 is equal to -1 and the K2 is equal to 2. And those are the two numbers that if you insert them in here, the result will be 7, 8, and 9. This is a very important question and usually repeated in plenty of quizzes and exams. Let's go to the span. The span is the generators of a vector space. So it's a group of vectors. I will have to search for them or I will choose them, and I will be able to use them, okay, these vectors, in order to generate any vector belongs to this vector space. What's the span? Let's say I have V vector space and it is with a certain dimension. If I have from V1 up to Vm vectors, okay, so V1 and V up to Vm are called, okay, a span if every vector of V can be a linear combination from the set. يبقى تاني once more, if I could use K1 V1, K2 V2, K3 V3 up to Km Vm, where K1 up to Km are real numbers, exactly like the previous problem. So this set, which is V1 up to Vm, it's called all of it a set of the span of vector space V, or the generators of vector space V. And this is stated in here, the set of linear combinations, V1 up to Vm is called the span, and V1 up to Vm also denoted by span V1 up to Vm, and they are the generators or the vectors that generate S or generate the vector space that you are interested in studying. Of course, you have all of these, I believe, the PDF of these lectures, I sent it to you previously. And also, I will send you this one too, to be with you. Okay, for example, if I say span of 1 and 2, I mean A times 1 and 2, where A belongs to R. So if you imagine A with all values belongs to R, يعني يا شباب يا مهند, A, it means the values from negative infinity to positive infinity. So imagine, for example, if I inserted A equal to 0, so the vector will be 0 and 0, which is normal, which is a requirement from the requirements of a vector space. If I put A equal to 1, you will have the form 1 and 2. If I insert A equal to 2, so I will have 2 and 4. If I insert A equal to half, so I will have exactly 1.5, I'm sorry. So the result will be as you can see. And all of that are a subset of R2. So actually, that's a span of a vector space. And this vector space is a sub-vector space from R2. In a similar manner, exactly, the span of the vectors or the coordinates in 3D, which has two vectors, 111 and 212, which can be considered as generators of a certain vector space just only by changing the multiple number or the scalar that's going to be multiplied by 111 and by 212. So A and B belongs to R, just to change them, and you will have all of this. So if I choose A and B equal to zeros, it's going to be the origin. If I choose A equal to 1 and B equal to 0, the result will be 1, 1, 1, 1, 1. If I choose A equal to 0 and B is equal to 1, I will end up having 2, 1, 2. If I put A equal to 1 and B equal to 1, so it's going to be 3 to 3. And all of this is considered a vector space, and also it's a sub-vector space from R3. In a similar manner, we can do this exact same thing with matrices. So for this matrix, for example, 1, -1, -1, and 1, if I multiply the elements by A and the A belongs to R, so I will have various versions of these matrices. Also, in a similar manner, if I have two of them and multiply the first by A and the second by B, I will have various shapes and various vectors or objects from this shape. So every span of a set is actually generation of a vector space. And all of these vectors are belonging either to R2, R3, to a set of matrices, square matrices with a certain dimension, or a set of matrices square, or a certain matrices which are diagonal, and so on. The proposition: if V1 up to Vn are vectors of a vector space V, then the span V1 Vn is a vector subspace of V. يعني لو انا عندي مجموعه من الفيكتورز بينتموا لفيكتور سبيس، يبقى السبيس او الست اللي هتبي formed from all of these vectors دول هيبقوا vector subspace of V. طيب if I have the span 1 and 2 vector subspace of R2, so it's gonna be just multiplying by the numbers, okay, as we did previously for 111, for 212, for the matrices, this matrix or another matrices. So exactly the same examples like what we did go through. Let's see how this system of equations will generate a vector space by itself. Let's look at this problem. If I took these two equations, and if you remark, that's a reduced echelon form for a system of equations of 3 variables and 2 unknowns. Actually, 4 variables and 2 equations. I'm sorry. If you look closely these two equations, you will find that x3 values equal to 0, while x1 value can be got from the relation between x3 and x4. So simply, I can send -3 x2 to the other side and x4 to the other side. So I would have the relation that x1 is equal to 3 x2 minus x4. And in a similar manner, x3 would equal to 0. For R4, or a set of vectors belongs to R4, it will contain 4 coordinates, x1, x2, x3, and x4. All I have to do is just to make this substitution. I will replace x1 by 3x2 minus x4 and replace x3 with 0. And that's gonna be the form of vectors that I'm going to find the generators of this vector space. So if you look closely, you will find the first component contains x2 and x4. The second component contains x2 only. The third component is equal to 0, and the fourth component x4. So let's count the variables. It's x2 and x4. I can separate this vector to two vectors. The first will be 3x2. Second coordinate gonna be x2. third coordinate is 0, and the fourth coordinate is 0, plus another vector, which is negative x4, 0 in x2, 0 in x3, and x4 altogether. So that's the shape that we are talking about. Taking x2 from the components of the first vector will leave you with 3, 1, 0, 0. Taking x4 from the second vector, it will leave you with negative 1, 0, 0, and 1. And those two vectors are the basis or the span of this vector space. So the span is 3, 1, 0, 0, negative 1, 0, 0, and 1. How many vectors do you have? We have two linearly independent vectors. And this is what we will talk about in the next slides. Okay, so these two vectors are generators of a vector space based on the values of x2 and x4, which belong to R. Here, the degrees of freedom is 2 degrees of freedom, and the dimension is 2, which is a subvector space from R4. This system, or this homogeneous system, have a very remarkable proposition. Let's see. The solution set of a system of linear equation is a vector space, if and only if. It's going to be a vector space, if and only if. The system is homogeneous. So I'm solving a system of equations, and the right-hand side will equal to 0. That's called an homogeneous system of equation. It is of the form Ax is equal to 0. I will continue with more uh, statements and more applications within the next slides. But for the time being, I want to go to exercises in order to reinforce the idea of a vector space, a subvector space, what linear combination, the basis, and so on. Of course, we will have lab application. I told you previously more than once. The lectures of Python is just an intro for you to help you to go to lab web page, which is an internet web base that will form a suitable environment for you and will help you to enter these codes and to see the results. It will be explained to you in certain lectures. I will try to coordinate me and the program director within the next, not the coming week, the week after, inshallah. Once we arrange for this, we will let you know. Okay, let's back again to the main part, which is with the linear algebra. Confirm that the following subsets are not vector subspace. أكد على إن the following subsets are not vector space. Of course, the question may not come to you in this statement, but he can ask you to prove that if this is a vector space or not a vector space, and so on. And we already had the first midterm, and you know it's going to be a multiple choice, and you have the quizzes, so it's going to be easy for you. He is asking you, confirm that the following subsets are not vector subspace of R2. So, from my understanding, there will be a failure in the conditions required for a vector subspace. What are the conditions? The closure of addition, the closure of multiplication by scalar, if you remember, and the existence of the same origin of the dimension that we are dealing with. So, first of all, you will have to check these 10 points, the addition part and the multiplication by scalar part. Then also I want you to remember the following. So W is said to be subvector space if and only if the origin of this set is exactly the origin of the vector space that belongs to mainly. So this is the first step. Second step, closure under addition and the closure under multiplication by scalar. Let's see the first question. We want you to check that for the set of x and y coordinates that belongs to R square, but such that in x is greater than or equal to 0 and y is greater than or equal to 0, which means we are going to test the set of points belongs to R2, but just only within the first quadrant. Those set in the first quadrant, where x is greater than or equal to 0 and y is greater than or equal to 0. Do you think these properties are going to hold? Let's discover. So that's the problem that we want to check, as I told you, that the set of xy belongs to R squared is a subset from this one. Brief step number one is to check the existence of the zero vector. And already exists, because if x is equal to 0 and y is equal to 0, the conditions state that, then I will have the origin within my set. So the first condition or the first step is considered. Closed under scalar multiplication. يا ترى ده closed under scalar multiplication ولا لا؟ Let's see. بالفعل, for any two values that exist in this in this quadrant, if the scalar is positive, you will find a point belongs to the first quadrant. For example, if I have 1 and 1, which belongs to the first quadrant, multiplied by 2, by 3, by 4, by 1,000, by 10,000, you will have exactly the values already exist in the first quadrant, but the existence of the negative value doesn't exist. So if you multiply by a negative value, you will have negative 1 and negative 1. Negative 1 and negative 1, it's not within this set. So this is one of the major failures in the multiplication by a scalar. So negative 1 and 1 doesn't belong to S, so it doesn't represent, it's not closed under scalar multiplication. So of course, it's not gonna be a subvector space, and that's the main reason. Optional, if we want to study the closure under addition, it will be closed. So the failure mainly is from the scalar multiplication, not from the addition. Also, the zero already exists. And all of this I've wrote it for you perfectly in order to make your life easier. Okay, for the second question, he wants you to check the set of all points that belongs to R2, but under the condition that x is equal to 0 and y or y equal to 0. It's a union symbol. So I'm talking about the set of all points which belongs to the x-axis and the y-axis. So the set description, x and y-axis is equal to 0 in the y-axis, and xy is equal to 0 in the x-axis. So I'm talking about the x and y axes. The set contains the zero vector, yes, because the zero vector belongs to the x-axis and the y-axis. Okay, condition number one is satisfied. Let's check the closure under addition. This is gonna be a failure in here, because if you have a point with 1 and 0 and a point in 0, 1 and added them together, you will end up having a point that's not belong to the set of points on the x-axis or a set of points on the y-axis. So it's not closed under this addition, and this is why it's gonna be a failure in the conditions required for a subvector space mainly. Of course, for the it is closed under scalar multiplication, because if you have a point belongs to either the x-axis or the y-axis and you multiply it by a number, the result will be on the x-axis and also on the y-axis if it already exists. I mean, if you have, for example, 1 and 0 multiplied by 1,000, you will have 1,000 and 0, which belongs to the x-axis. If you have 0 and positive 2, and you multiply it by 4 or by 8 or by 6, it will be the same shape. So this condition satisfied, failure will be mainly from the under the addition process. So now you can see that number A failed because of the scalar multiplication, and number B is failed because of the addition failure. Of course, it's why it's failed. I also wrote it for you. Okay, he's asking you which sets are vector subspaces of vector space of real matrices n by n. So I'm talking now about the set of matrices, square matrices, And I'm discussing these special cases. Number one, the set of diagonal matrices of order n. And this is really very easy. Yes, it's a diagonal. It's going to be, it will represent a subvector space. And also, from all the vector spaces, a subvector space from all the vector spaces of the square matrices. The zero matrix is diagonal. Okay, some scalar multiplies of a diagonal matrices are diagonals. If you have two matrices, adding them together will be a diagonal matrix. Multiplying by a number, it will be a diagonal matrix. This is called under addition and scalar multiplication. So hence it's a subspace. Same way for the idempotent matrices, it's not gonna hold. Because what's the idempotent matrices? We saw a very good question about the idempotent matrices, where a square is equal to a. Then if you have c times a square, it's gonna equal to c squared times a, which is a failure in the multiplication by a scalar, so it's not gonna be a subvector space. For the set of symmetric matrices, yes, it represents a subvector space. It's really very simple because the zero matrix is symmetric. If A and B are symmetric, then the addition will be symmetric. And also for the transposition position, it will be the same. So it is closed under addition and scalar multiplication, and it makes a very good sense. Also, for this problem, which is 213, one of the very nice problems, he's giving you S, which is U, V, and W. He gave you U, negative 1 and 1, V, 1 and 1, W, 2 and 1. Those are three vectors, and he is asking you, find the linear combination of the vectors in S whose coefficients are 3, 1, and negative 2, which is really with the same order, which is really a very simple. All I have to do is to write the linear combination with 3 times u, 1 times v, negative 2 times w, and I will be able to get a new vector, which is negative 6 and 2. So negative 6 and 2, simply, it's a linear combination from these three vectors. Also, he is asking you to find coefficient for a linear combination of vectors in S that result in 1 and 3. So he needs you to show us how 1 and 3 is a linear combination from U, V, and W. And we already saw problems like this in this session and in the previous session. All I have to do is to form this system of equations. So first vector, first column times A, second vector times B, third vector times C, and equal to 1 and 3, the vector that I want to find the coefficients that will generate it, which is really very simple. Now I will have to solve this system. Let's get back to an augmented matrix, having negative 1 and 1, 1 and 1, 2 and 1, and 1, 3, and try to work out this augmented matrix in order to be as near as possible to a reduced echelon form. That's the reduced echelon form, which implies that A will equal to 1 plus half of C, and Y will equal to 2 minus 3 of 3 over 2, 2 minus 3 over 2C. And those are the components. I will replace A by 1 plus half of C, and also the second component B will be 2 minus 3 over 2C, and those are the forms of the vector. All I have to do is just consider C or T is a value with respect to R. So if I used T equal to 0, I will be able to have that A with B with C as a combination 1, 2, and 0. So actually vector 1 and 3 can be generated considering A is equal to 1, B is equal to 2, and C is equal to 0. You can choose T equal to 1, which is going to lead to another 3 numbers, and also will make this equation correct. And if you check, it is correct 100%. Okay, for this problem, he's also exactly like the previous one. He is giving you a set of U and V. U and V vectors already exist. He's asking you to find the linear combination of vectors in S whose coefficients are 3 and 2. So multiply this by 3 and then by 2. If possible, get the coefficient as linear combination of these two vectors we are repeating the same problem exactly. It is also exactly the same. That's a set of three vectors. And I want to have to show that or to find the variable, the coefficient that will make it equal to 2, -1, and 6, or how to generate 2, -1, and 6 from these three vectors, and also exactly the same. So I will use mainly the relation of the linear combination. In this question, he is asking you, for each case, find the set of vectors that generate the following vector subspace. He gave you the S subset, which contains, that's the first component, second, third component, where A and B, such that where A and B belongs to R. All I have to do is to make the substitutions to be able to generate. Let's see what he needs. He is asking you, find a set of vectors that generate the following vector subspace. Okay, very good. Try to separate these vectors or this set. Let's do the first problem. And the rest will be exactly the same. The first problem, I have 3a plus b, a minus 5b. So I will look to the first component, which contains a and b. The second component contains a only. The third component contains a minus 5b. And then I will try to separate the a by itself and the b by itself. It's going to be 3a, first component. Second component is going to be a. Third component is going to be a, and that's for the first vector. For the second vector, it's going to be b. There is no b in the second coordinate, so it's going to be 0. -5b, so it's going to be -5. And those are the two vectors that will be generated from this vector. So the two main vectors, which are 3, 1, 1, and 1, 0, -5. Now I have the generators of this vector space, which are these two vectors only. And so I can generate any vector or belongs to this subvector space just only using those two vectors. So the set of, or the span of this vector space is 3, 1, 1, and 1, 0, and -5. And it contains just only two vectors. This is also exactly the same. There is no new steps in this problem. Here he wants you to check. I found that this problem is a very nice one about this question. He's asking you to state, is it true or false? If V is a solution of AX equal B, then 2V is also a solution of this system. Let's think. If AX equal to B, then V, I'm sorry, is a solution for the system AX equal to B. Then also 2V is a solution of this system. I guess it's partially true. Because if it is a unique solution system, a Cramer system, which have just only one solution, this is not going to be correct. But if this is an infinite number of solutions, the result will be correct. I've wrote the answers for you in here. That's if AV equal to B. If I inserted 2V, so I should have E to V, which is 2 times AV. And this must equal to 2B. While the actual answer is A, or the question is asking if AX equal to B and the V is a solution, then 2V is also a solution, which is a contradiction. It will happen only when B is equal to 0, or that's a homogeneous system. And it is already in front of you. That's the Python exercise, and it's supposed to be a very direct one according to the previous training. Thank you very much for listening to this lecture. Please feel free, if you have any comments, just send them to me under this video, or just send me through the WhatsApp. In all times, I'm really very happy to be with you and to assist you. Thank you very much, and enjoy a wonderful day. Thank you. Bye bye.